Welcome to this comprehensive masterclass on one of the most fundamental yet frequently misunderstood distinctions in statistics: standard deviation versus standard error. While they sound similar and are mathematically related, they serve completely different purposes in data science, medicine, and engineering. Understanding this distinction is the hallmark of a true data expert. Let's start with the standard deviation, or SD. The standard deviation is a measure of spread. It tells us how much individual data points in a single population or sample vary from the mean. If we measure the height of every player in a basketball team, the SD tells us how much the height of one player typically differs from the team's average. High SD means the data is widely dispersed. Low SD means the data is clustered tightly around the average. Technically, the formula for the population standard deviation is the square root of the variance. We subtract the mean from each observation, square the result to eliminate negative signs, sum them up, divide by the number of observations, and finally take the square root to return to the original units. This value represents the typical distance of a data point from the center. Now, let's shift our perspective to the standard error, or SE. The standard error is not about individual data points, it is about the precision of an estimate. Usually, we refer to the standard error of the mean. It tells us how much the sample mean would fluctuate if we were to repeat the experiment many times using different samples from the same population. It represents the uncertainty in our estimation of the true population mean. Imagine we are conducting a study on the average salary of software engineers globally. We can't measure everyone, so we take a sample of 100 people and calculate their mean. If we take another sample of 100, the mean will be slightly different. The standard error is essentially the standard deviation of these sample means. It quantifies how much sampling noise is present in our study. The mathematical relationship between them is vital. The standard error is the standard deviation divided by the square root of the sample size, denoted as n. This formula reveals a critical insight. As your sample size increases, the standard deviation of your data stays roughly the same because the underlying population doesn't change, but your standard error decreases. More data makes your estimate of the mean much more precise. To visualize this, imagine a bell curve representing the population. The SD describes the width of this curve. Now imagine the sampling distribution of the mean. This is a much narrower curve centered at the same spot. The width of this narrower curve is the standard error. As n grows, this secondary curve becomes a sharp spike, showing that our confidence in the average is extremely high, even if individual variation remains large. When should you use which? If you are describing the natural diversity of a group, such as the range of blood pressure in a healthy population, use standard deviation. If you are reporting the reliability of your research results or constructing confidence intervals to show where the true population parameter likely lies, you must use standard error. A common error in scientific literature is using standard error to describe data variability because SE is always smaller than SD, making the data look cleaner or less noisy. This is statistically misleading. SD describes the who, the individuals, while SE describes the what, the accuracy of the mean. Confusing them can lead to overconfidence in unstable data or a misunderstanding of biological or physical diversity. In conclusion, the standard deviation is a descriptive statistic. It describes the sample. The standard error is an inferential statistic. It allows us to make leaps from our sample to the general population. Mastering this distinction ensures your analyses are robust, your charts are honest, and your conclusions are scientifically sound. Thank you for joining this deep dive into the heart of statistical precision. References: 1. Gujarati D.N., Basic Economics. 2. John E. Friend, Mathematical Statistics with Applications. 3. Altman D.G. and Bland J.M., 2005, Standard Deviations and Standard Errors, BMJ. 4. Rice, J.A., Mathematical Statistics and Data Analysis.